Welcome back to my SlideCast of the lecture I gave at the SoTiC meeting in Trondheim. In this part B, I want to talk about flame flow feedback and in particular the effect that convective velocity perturbations and the resulting flame displacement play in this effect. I think flame flow feedback is a very fascinating topic that deserves more attention than it has received so far. There's a lot of interesting flow and flame feedback. Convective velocity perturbations were first discussed by François Bayot and Anne Birbeau. They measured the velocity field inside of the flame cone of a laminar flame with PIV. And they observed in particular at low Struhal numbers that there are perturbations of velocity that do not travel with the speed of the flow, but that are significantly slower. The effect of these perturbations on flame shape and flame heat release are illustrated in this cartoon here that was prepared by Thomas Steinbacher. Then a few years later, Thierry Schuller also included more or less ad hoc convective velocity perturbations in his G equation-based models of the flame transfer functions. Those convective perturbations were introduced to obtain the correct phase, a phase of the flame transfer function in agreement with experiment. The origin was not discussed at length in those papers, but Blanchard and colleagues also, Thierry Schuller and Thierry Poisson, had more solid results obtained with a linearized reactive flow model. And the picture you see on the right is from the paper of Blanchard et al. And here the idea expressed is that wrinkles of the flame generate vorticity, and the vorticity then induces velocity perturbations, which in turn further influence flame shape and surface area and heat release rate. So we also looked at this, but with a slightly different approach. In particular, Thomas Steinbacher built a dynamic model of a flame as a combination of several ingredients. First he had a model for the flow as a sum of irrotational and rotational components. So he did not simply impose a presumed functional form of the velocity perturbation, but tried to model this with, on the one hand, potential flow models, and secondly, with velocity resulting from vorticity. And in particular, he concentrated on two possible sources of vorticity, and that is resulting from flow separation and resulting from flame wrinkling, indicated by the little blue whirling thing near the tip of the flame here. Secondly, he had a 2D G equation model, so that described how the flame responds to the flow. But the G equation model could also be supplemented by a flow-flame interaction, for example, by vorticity generated by wrinkles or by throwing in volume sources along the length of the flame. And the advantage of this combination of building blocks was that one could turn on and turn off several contributions and assess their relative importance. In particular, Thomas compared then a unidirectional model where the flame affects the flow, but not vice versa, with a bidirectional model that also includes flame flow feedback. But first, one more slide that illustrates how the flow was constructed. We used old school Schwarz-Christoffel mapping that gave us inviscid and irrotational flow, potential flow, and then a Kutta condition was attached to the corner, as shown here, which generated vorticity, which was then transported by the potential flow into the combustion chamber. And from the vorticity through BU Savar, we also had a solenoidal velocity field. Now what you see here is a movie, an animation of the unidirectional model. So only flow, as described, from Schwarz-Christoffel and Kutta condition acting on the flame. And what you see on the top half is, on the one hand, that street of vortices with alternating signs, positive and negative, starting from the Kutta condition, from the sharp corner, the velocity field resulting, induced by the vorticity, and the perturbation of the flame shape induced by the vorticity. The lower half then shows the potential flow computed with Schwarz-Christoffel and the impact that the potential flow has on the flame shape. And if you compare the two halves of the picture, you see, and that came to me as a surprise, that the vorticity hardly affects the flame shape, and it is mostly the potential flow that acts on the flame base, pushes at the flame base, and the wrinkles generated there are then convected by the mean flow towards the tip of the flame. Now, comparing the flame shapes obtained with this model against CFD gave very significant discrepancy. That is what you see here. So mind you, this is the flame shape, not the impulse response. So the shape of the flame after an impulse perturbation of the velocity. That impulse perturbation has a potential component that displaces the flame base towards larger radii. And you see here this sudden increase in displacement towards large values for, well, actually all three models that we observe here. The three models are the unidirectional model that I've just described, red dashed line. The blue line is in the bidirectional model, which includes flame flow feedback through vorticity generated by wrinkles of the flame. And then the black line is a CFD model of a 2D laminar flame with a confinement ratio of 0.4. Now, at the initial time, after the impulse kick has displaced the flame base, all three models agree more or less. Then the unidirectional model shows a behavior that this initial perturbation is flame shape, or flame shape is transported convectively towards the tip, and the original flame shape is restored. This is in pronounced contrast to the CFD results, which show that there is also then an inward movement on the one hand of the flame, and more relevant perhaps also a growth in perturbation amplitude. Watch the black line evolving as a function of time. Now that behavior is completely missed by the bidirectional model. At late times we have very significant disagreement. The bidirectional model, on the other hand, which includes flame flow feedback, does a pretty decent job considering the simplicity and the degrees of modeling that one has in these models with the CFD results. So the important contribution is that the bidirectional coupling, which gives rise to convective velocity perturbations, is obviously very important in obtaining the flame shapes and thus the heat release rate of a laminar flame. And this is now described here. Here you see on the left the impulse response and on the right the flame transfer functions obtained again with those three models. And again we see that the unidirectional model fails qualitatively, does not produce excess gain. However, the bidirectional model, which includes the effect of vorticity and the solenoidal field generating additional velocity contributions inside the flame cone. So the important contribution here would seem that convected velocity perturbations do not directly result from acoustic to hydrodynamic mode conversion, but they are generated by flame flow feedback, and they have a very pronounced impact on the flame dynamics, that is the flame heat release rate. And the question is, does the convective velocity model of the G equation as we know it, does that misrepresent causality? Next, I want to discuss fairly briefly inertial waves, formerly known as swirl waves. And the mechanism is described in this sketch, which I've taken from the paper from Grégoire Varillon. And the idea is here, as an acoustic wave passes over a swirl generator, it generates perturbations of the azimuthal velocity. And then the azimuthal velocity, this was originally hypothesized by Richard Straub and Douglas Straub and Geo Richards. And those swirl propagations then somehow modulate the heat release rate. How that comes about has not been clarified yet, because if you have an azimuthally symmetric flame, azimuthal velocity perturbations would have a hard time perturbing the flame. And it was Alp Al-Bayrak in his work who worked out that we shouldn't think of swirl waves simply as perturbations of azimuthal velocity that are transported by the mean flow, but instead we should discuss the propagation of inertial waves. And inertial waves result from an exchange between radial pressure gradient and centrifugal forces and the constraints of mass conservation. This is explained, for example, in the paper by Grégoire Varillon, which we hope to publish this year. And the important thing about inertial waves, then, they also have components of the radial velocity and the axial velocity. And those components then can directly interact with the flow. They can bring the flame out of kinematic balance and start changing flame angle, flame surface area, and so on and so forth. And Grégoire's work in particular further analyzed the generation of the hydrodynamic instability and the longitudinal acoustics with modern tools of hydrodynamic stability analysis, in particular resolvent analysis. So that's all I wanted to say at this point. Part C then will discuss the generation of entropy waves by heat release.